Hello again. In my last talk I mentioned that planets around other stars are pretty common, though for years astronomers had actually debated this, and in fact it wasn't until 1992 that the first so-called exoplanet was confirmed as such. Since then, the discovery of exoplanets has become something of a growth industry. We now know of thousands of them, so the debate has moved on. How many out there are like the Earth and could be habitable? In fact, what we now want to know is the Earth alone? Before we start looking for these so-called exoplanets, I want to spend a bit of time to understand our own solar system. So, here goes. What you're looking at is a diagram of the distances of the planets from the Sun. Okay, so these are all rather crammed together, all the rocky planets. And you see that Jupiter varies a bit in distance from the Sun, Saturn a bit more, Uranus even more, and the dwarf planet Pluto varies by huge amounts. So this means that their orbits are not exactly circular. In fact, they're elliptical, and some are very elliptical. Some of the other planets out there in the Kuiper belt are hugely elliptical orbits. The other thing to notice about this is what the planets are made of. All down here, Mercury, Venus, Earth and Mars, they're all rocky planets, terrestrial type of planets in a way. Then we have the asteroids, which are also rocky, but then we mentioned a set of planets which are gaseous, largely. Now, the general idea, at first glance, this arrangement makes sense. Planets that formed close to the Sun are low in what's called the volatile elements, things like hydrogen, stuff that's easy to sort of boil off and go away if you're close to a star. Whereas those that form further out, Jupiter, Saturn, Uranus and Neptune, are rich in these elements, hydrogen for example, the gas giants. However, it's not actually quite so simple as that. This is what is thought happened as the solar system formed. Really, the first large planet to form, the first planet to form, was Jupiter. Jupiter is very big, and this forms out of the material in that disk of material that was circling around the new Sun. But interactions of Jupiter with that disk actually cause Jupiter to spiral inwards towards the Sun. And so we find that after 70,000 years or so, Jupiter is really quite close to the Sun and getting closer. And in fact it would probably continued getting closer had it not been for Saturn. We get another largest planet forming out there, and Saturn in the same way starts to migrate inwards towards the Sun. And being a bit smaller, it actually goes a bit faster. And so it caught up with Jupiter and eventually ended up in what's called a 3-to-2 resonance. That is, Saturn, went twice round the Sun for every time that Jupiter went 3 times round the Sun. Now that interaction, the gravitational interactions between those two, then actually caused both planets to move back outwards again, causing more disruption in the solar system, eventually reaching their present positions. Now actually the disruption of that disk of material around the Sun, caused by Jupiter and Saturn wandering around, actually resulted in some volatiles being available to the rocky planets, and it also depleted material near Jupiter, which actually meant that Mars was probably smaller than it would have been otherwise. Now, in fact, when we look at extrasolar systems, planetary systems around other stars, quite a lot of those have what are termed hot Jupiters, that is, large gas giants, but actually positioned quite close to their stars. And presumably, these formed further out and then migrated inwards, and without an equivalent of Saturn, they never moved out again. So, it's possible that our solar system may not be typical. However, now it's time to consider how we actually detect planets outside our own system. And the main difficulty is that planets are actually very faint. You can't normally directly image them. They're too faint to see against the glare of their star. So how do we find them? Remember from my talk on starlight that if you shine the light of a star, or the sun, through a prism, it splits the light into its component colours and you get what's called a spectrum. Something like this. And recall also that the dark lines crossing the spectrum, called absorption lines, and that they can be used to find out which chemical elements are present in the star. But for now we're interested in another use for them, and that is to measure the star's speed. If a star is moving away from us, then the lines actually shift towards the red, rather than being in their normal positions. If the star is moving towards us, they shift towards the blue, an effect that's called the Doppler shift. It also happens with sound. Now, we can use this to measure how fast the star is moving, either away from or towards us. How does that help us? It's often said that the planets in our solar system orbit around the Sun, but this isn't strictly accurate. The planets and the Sun orbit around the centre of mass of the solar system, and the position of that centre of mass is dominated by the Sun and by the largest planet, Jupiter, which you remember is 2.5 times the mass of all the other planets combined, although the other planets do actually contribute a little bit. So the centre of mass of the solar system actually moves around depending where Jupiter and the other planets are, and in fact quite often it's outside the Sun altogether. And you can see on this picture how the centre of mass has moved through various years in the sort of 1950s to 1990s. And you see that most of the time it's actually outside the Sun. So, centre of mass moves around. Now that means that the Sun, which also has to orbit around the centre of mass, appears to wobble. It actually moves a bit. And viewed from afar, say from another star, that means the Sun will seem to move away and towards that star depending on where the centre of mass is at the moment. And that will shift the lines in its spectrum. So somebody at that distant star will be able to deduce the existence of planets around our Sun by noting the shifts in the spectral lines. And in fact, the first exoplanet orbiting a Sun-like star was discovered using just this method in 1995. Although it has to be said most have been discovered by other means, which I'll come to shortly. And that planet that was Earth-like planet that was first detected is going round the star 51 Pegasi. And here's some results from it. And this is the velocity, the speed at which the star is moving towards us or away from us. and you can see how it regularly varies over a period of a few days. And in fact the maximum velocity is about 80 meters per second, either towards us or away from us. Now this planet is actually relatively easy to detect because it has a large mass. It's actually about half that of Jupiter and is also very close to its host star. Okay, it's about 20 times closer to its star than the Earth is to the Sun. But most planets, as I said, are discovered using a different method to this. Here's a simulated picture of Jupiter, remember the largest planet, crossing in front of our Sun as viewed from a distance. And it's called a transit. Okay, and you can see that it blocks out some of the Sun's light. So, viewed from another star, the Sun's brightness would appear to decrease whilst Jupiter crosses the Sun, and then increase back to its normal value again afterwards. And in fact, most exoplanets have been discovered using this method. They've discovered thousands in this way, rather compared to, say, the hundreds using the shifts in the spectral lines. And here's an example of the brightness changes caused by 3 planets orbiting the same star. The changes are very small. You can see the figures here. But they're clearly detectable. From these curves, we can tell the duration of the planet's orbits, how long they take to go around their star, and get a good estimate of their size. Now, of course, if a planet doesn't happen to pass in front of its star as seen from the Earth, we'll not detect it using this method. And many planets will be missed because of this. For planets around the Earth's distance from the Sun, probably less than 0.5% of them will be suitably aligned. Another problem with this method is the rate of false detections. For the Kepler spacecraft, which has detected thousands of planets using this sort of transit method, okay, it's reckoned that it might have something like 40% of its detections are false for single planet systems. So you've got to confirm the planets using a different method, usually that one I've just talked about, the actual shift in the spectral lines, the so-called radial velocity method. Although it's reckoned that for multiple planets in the solar system, the false positive rate is much lower. Now, Kepler, the Kepler mission, looked at a very small area of the sky. However, there's a more recent mission called TESS, which is looking at nearby stars over the whole sky, some 200,000 of them. And I'm going to show you a video describing this mission. It's longish, but it gives an idea of the sort of complexity that's involved in these sort of missions.
TESS, Transiting Exoplanet Survey Satellite, discovering new Earths and super-Earths in the solar neighborhood. TESS has a simple stair and step observation strategy. TESS points anti-solar and remains fixed in inertial space for 27 days or 2 orbits. TESS is a 2-year all-sky survey mission with 26 observation sectors or 13 sectors per year. The overlap of the observation sectors near the pole is optimized for JWST's continuous viewing zone. After completing the Northern Hemisphere in Year 1, TESS transitions to map the Southern Hemisphere in Year 2. Every 13.7 days, TESS orients to point the Ka-band high-gain antenna towards one of 3 DSN stations for science data downlink. After the nominal 3-hour downlink is complete, TESS reorients back to science mode. Following the launch from Cape Canaveral Air Force Station, TESS is placed into a 600-kilometer parking orbit. The lower adapter structure is released from the solid rocket motor. The satellite and the SRM stack spin rate is increased to 60 RPM. The solid rocket motor ignites, sending TESS into its first phasing orbit with a nominal apogee of 250,000 kilometers. The solid rocket motor burns out, and the spent rocket motor is released and falls away. TESS despins using onboard thrusters. TESS deploys its solar panels. TESS has only one deployment. At phasing orbit perigee, TESS performs a burn to increase apogee. TESS uses lunar gravity assist for mission orbit insertion. Following the lunar flyby, the TESS transfer orbit has a nominal lunar inclination of 37 degrees en route to Plie. At PLEP, TESS performs the period adjust maneuver to reduce the mission orbital period to be 13.7 days, a 2-to-1 resonance with the orbit of the Moon. Lunar perturbations are roughly averaged to 0, with the Moon leading or lagging TESS at apogee by 90 degrees. The helioorbit is stable over decades. TESS will discover new Earths and super-Earths in the solar neighborhood.
In April last year, NASA announced that TESS had detected its first Earth-sized world, HD 21749c, and that planet is about 89% of the Earth's diameter and orbits a K-type star about 53 light-years away. That star is about 70% of the Sun's mass. Remember, the Sun is of type G. This is the second planet that TESS has identified around this star, and it completes one orbit in just under 8 days, so it's actually very close to its star and therefore should be very hot, maybe as hot as 430 degrees. As of May this year, TESS has discovered 46 confirmed planets, and there are about another couple of thousand awaiting confirmation. Also up there is the European CHEOPS mission, which has also started characterising exoplanets that have previously been discovered. And finally, in case you were wondering that whether there are some direct images of planets, yes, there are. This was taken in September 2008 and shows 3 out of the 4 planets around the star HR 8799. Again, the image of the star has been removed so that you can see the planets. And observations over time show that the planets are all moving anti-clockwise around the star. All of them are actually quite young, 60 million years or so, and so are still partly self-luminous. They're still hot. They're also large, in the range 7 to 10 Jupiters, and about between 25 and 70 times the distance of the Earth from the Sun. For comparison, Neptune in our own solar system is 30 times the distance. So direct imaging like this, and also this previous transit method, in principle allows the atmospheres of the planets to be studied. But currently only a handful can be actually done in this way, most of which are large, hot, gas giant planets. In 2016, the Hubble Space Telescope detected hydrogen and helium and maybe hydrogen cyanide, but no water vapour, in the atmosphere of a planet around the star 55 Cancri, a super-Earth. Another example is what has to be said the latest Hell House planet, Kelt 9b in Cygnus, which has an atmospheric temperature of 4,000 degrees centigrade on average, and which actually contains vaporised iron and titanium. And for a few planets, clouds have also been detected. Alright, enough about the techniques. What about the results? This shows the total number of exoplanets confirmed up until late June this year, and it's their cumulative totals, so they keep going up. And this sort of burst of activity when things went up very rapidly are largely due to the Kepler mission. So, as at the beginning of July this year, 4,281 planets have been confirmed in 3,163 planetary systems, with 701 of those systems having more than one planet, and there are still a few thousand awaiting confirmation. In fact, recent observations of nearby stars imply that the vast majority of them have one or more planets. And you can see from this graph that most of them have been detected using the transit method, that's the green bits. But what we're interested in for this talk though are Earth-sized planets. So how many of those are there? Well, here's a plot of exoplanet sizes against distance from their parent star. And first of all, let's make it clear that it's very unlikely that this represents what's really out there. There are what are called selection effects at both ends of the size scale. Small planets are much more difficult to detect, and large Jupiter-sized planets with long period orbits, i.e. a long way out from their star, are also less likely to have been discovered. However, looking at this, most detected planets are in the super-Earth to small Uranus type size scale. Okay, so we're up this sort of range. Earth-sized planets, which are down here, are rarer but not uncommon. But how many of these are in the so-called habitable zone? And by habitable, I mean the range of orbits around a star in which a planet could have liquid water on its surface given a suitable atmospheric pressure. The planet is also required to be rocky and obviously capable of having an atmosphere. In other words, somewhere where life as we know it could exist. The planet Tess discovered, for example, it was a quarter larger than the Earth that I mentioned earlier, is in its star's habitable zone. Now, clearly the size and position of this zone depends on the temperature and the brightness of the star. And here's a diagram showing some of the current crop of exoplanets and their stars together with the Earth, Mars and Venus. So here's our solar system. And you can see that the Earth is in our star's habitable zone, as we may have already thought. Mars is also in it, just about. Venus, however, is just a little bit too close to the Sun. It's too hot. And an interesting one down here, Proxima Centauri, the nearest star to the Sun, also has this planet in its habitable zone, at least in theory. Now, based on the discoveries so far, we reckon that about 1 in 5 Sun-like stars are expected to have an Earth-sized planet in that star's habitable zone. And in fact, a recent study has suggested slightly better figures, around 1 in 4. So, we can try and extrapolate from that as to how many we'd expect in our own galaxy. The Sun is one of around 200 billion stars, maybe more, in our own local galaxy, the Milky Way. So if you extrapolate that 1 in 5 figure to the entire Milky Way, it means there could be 11 billion potentially habitable Earth-sized planets in our galaxy. And if we include red dwarf stars, like Proxima Centauri, that could go up to 40 billion. Red dwarfs are very common. Has to be said, though, that red dwarf stars, like Proxima Centauri, are prone to producing frequent giant flares. The Sun has flares, but they're quite minor in comparison with what red dwarfs can do. Proxima Centauri, for example, recently released a flare so powerful that that otherwise really faint star became visible to the naked eye on Earth. And the exoplanet around it is only a 20th the distance of the Earth from the Sun from its star, so really it's quite likely to get cooked by these flares going off, which means life will be somewhat less likely. Alright, so we're saying maybe 11 billion in our own galaxy. So let's extrapolate even more and go to the entire universe. Now, it's currently thought there are somewhere in the region of 2 trillion galaxies in the observable universe. So a conservative estimate of the number of Earth-like and habitable planets in the observable universe is something like this, about a quintillion. Which then leads to another question. How many of these actually do have life on them? And on what fraction of those would that life have developed to the stage where we would call it intelligent? Let me introduce you to the Drake equation. Now, this was formulated by the radio astronomer Frank Drake in 1961 in connection with the search for potential radio signals from extraterrestrial civilizations. And it's really more an attempt to promote discussion, but it is a useful means of expressing the problem of detecting intelligent life somewhere else in our galaxy. Let's have a look at what it actually shows. N here is the number that we're interested in. Is the number of technologically advanced civilizations in the Milky Way galaxy. Technologically advanced, something like ours, say. And that's going to be equal to the star formation rate times the fraction of those stars that actually have planetary systems times the number of planets per solar system which are habitable, which have an environment suitable for life, as it says here, times the fraction of those on which life actually does develop, times the fraction of those on which that life develops intelligence, as we define it, times the fraction of the civilizations that develop a suitable technology that releases detectable signs of their existence out into space, radio waves for example, times the length of time that such civilizations exist. Let's try and put in some numbers. The star formation rate. Well, we know this quite well. It's 1.5 to 3 per year, so let's call it 2. Fraction of stars with planetary systems. Well, it's looking like this is pretty close to 1, so I'm going to put in 1. The average number of planets per star having planets that might support life. Well, we've got this 1 in 5 figure for Sun-like stars with an Earth-sized planet in the habitable zone, so which would suggest about 0.2 for this value. Now, star doesn't necessarily have to be Sun-like or the planet Earth-sized, and it still might develop life, so it might be higher, but we'll stick with 0.2. Times the fraction of planets that might support life that actually go on to do so. Well, life on Earth appears to have developed as soon as favourable conditions arose, but I've got to admit that the sample size is small, and we might be atypical. So, in truth, we've no idea. I'm going to say 0.1, which some might say is optimistic, but planets are a lot more common than previously expected, so I'm going to go for the same for life. Next factor, the fraction of planets with life that actually develop intelligent life. Now, this one's really controversial. Estimates vary from almost 0 to approaching 1. So I'm just going to take a wild guess and go for 0.1, although I must admit I can't really justify that. Right, how many of those, what fraction of those with intelligent life reveal their existence via release of signals like radio waves? Well, the Earth reveals its presence in this way, although with our present technology we'd struggle to be able to detect ourselves even from the nearest star. Frank Drake reckons that this had a value of about 0.2, so I'm going to stick with that. Finally, times the lifetime of such a civilization during which it sends signals into space. Well, for us so far, this is around 100 years. Modern civilizations last on average for about 300 years, but wouldn't necessarily lose the technology. So, for the sake of argument, I'm going to say about 1,000 years. So we can now plug a value in for n, the number of civilizations in our own galaxy with whom we might be able to communicate. So that's 2 times 1 times 0.2 times 0.1 times 0.1 times 0.2 times 1000, which is 0.8. That's kind of ourselves, isn't it? Now, it must be said there are a lot of these numbers are fairly arbitrary. A lot of them we have no idea what the values are. And in fact, other estimates of n can really be quite big. They vary up to 15 million or practically 0. Okay, the former would imply that we're currently alone, and the latter leads to another problem, but we'll come on to that shortly. A recent paper, using somewhat refined assumptions and recent data, suggests that the value of n, is somewhere between 4 and 211, with the most likely figure being 36, which is surprisingly accurate. And this is, they say, a conservative figure because it's based on how long our civilization has been sending out signals, i.e. 100 years. If the 36 civilizations were spread out evenly throughout the galaxy, that would mean the closest would be about 17,000 light years away, which would make communication with them rather tedious. At the other extreme, if we're down at this 15 million or even much higher numbers, if there's this huge number of civilizations, as I said, then we have another problem, the Fermi paradox. And that is, if intelligent life is common in the galaxy, why haven't we detected any evidence of it? Which means we need to talk about SETI, the search for extraterrestrial intelligence. Now, this actually dates back to as early as August 1924, when for 36 hours an attempt was made to detect any radio signals from hypothetical Martians. Nothing was found. Modern SETI started in 1960 with Frank Drake, the Drake equation, and Project Ozma, and that used this 26 metre, that's 85 foot telescope at Green Bank in West Virginia in America. And he tried to detect any radio signals from around the stars Taur Ceti and Epsilon Eridani. Now consider the problem for a moment. Not only is there the whole of the sky to search, but there's also the whole of the radio spectrum. Radio telescopes are only sensitive to a very narrow part of this at any one time. So to try and narrow things down a bit, Frank Drake decided to look only around the frequency of 1420 megahertz. That's a wavelength of 21 centimetres. And the reasoning behind this was that neutral hydrogen atoms out in space radiate near this frequency. And so it could be regarded as a sort of universal marker frequency. An extraterrestrial civilization deliberately trying to signal might well choose this frequency. There again, it might not. Anyway, Project Ozma, nothing was found. In the 1960s, both Soviet and American scientists took an interest as well. The Big Ear telescope here in Ohio was working by 1963, although it was dismantled in 1998. And in 1973, it started a SETI program, again at 1420 megahertz. And on August the 15th, 1977, a signal was detected. The characters here on this represent signal strength, and this is the WOW signal. And it was detected from the direction of the constellation Sagittarius near the centre of our own galaxy. The signal was narrow band, that was less than 10 kilohertz wide. It lasted for the entire observing interval, which was 72 seconds. It was of uniform strength during that time, and it had no apparent modulation on it. Unfortunately, it has never been repeated. And currently there is no accepted explanation of this signal, but without any replication it cannot really be accepted as a credible detection of extraterrestrials. Since then there's been various search programs. The Allen Array, funded by the SETI Institute, currently has 42 antennae, and they hope to expand it up to 350, and that became operational in 2007. In 2015, $100 million was made available by the Breakthrough Listen initiative to buy thousands of hours of large radio telescope time over the next 10 years. And the Chinese 500 metre fast radio telescope, which is shown in this picture, actually has SETI as part of its science mission. And there have also been attempts to detect optical signals, if some civilization was trying to communicate using lasers. However, so far, all observations have drawn a blank. What about other attempts? Well, the star KIC 8462852, Kepler in Cygnus, known colloquially as Tabby's star, has large and apparently random brightness fluctuations. And somebody suggested that these might be caused by what's called a Dyson sphere around the star. And these things were originally suggested by physicist Freeman Dyson in 1960. He died recently, actually. And this is an artificially constructed sphere of light traps around a star intended to gather energy for an advanced civilization. And they'd have to be pretty advanced to do this sort of thing. However, the most likely explanation is that the variations are natural, even if we don't currently understand the mechanism. SETI observations have been carried out of this star, and, as usual, nothing was found. Now, it may have occurred to you that if everybody is listening and nobody is transmitting, then that might explain why we've heard nothing. Well, we have sent things like this record out. This was fastened to both of the Voyager spacecraft, but they won't go anywhere near another star for another 40,000 years, and even then the closest approach will be about 1.5 light years. The first radio message deliberately sent out by us was in 1974, and it's towards the globular cluster M13. But we couldn't expect any response from that for tens of thousands of years. In 1982, 2 Japanese astronomers sent a message in the direction of Altair. The earliest that a reply could have been expected to that was around 2017, but I don't know if anybody was listening. The next soonest will be from a star in Aries sometime in the 2030s. So all in all, we actually sent out over 30 deliberate signals, although it has been questioned, should we have? But even without these, could an advanced civilization have detected us anyway? So far, our normal radio broadcasts have reached around 100 light years out into space. The pale dot in this picture. Now, by the time one of our broadcasts had reached even 20 light years away, it's going to be billions and billions and billions of times weaker. The signal spreads out as it moves. So it's going to be very hard to distinguish from simple background noise. Although it might be possible to pick up some of our radars from hundreds of light years away if the aliens happen to be in the beam and also listening on the right frequency and in the right place and the right time. In 2008, NASA actually transmitted some Beatles music appropriately across the universe towards the pole star Polaris. That's 430 light years away. They used 18 kilowatts of power into a 70 metre antenna. It's reckoned that any aliens out there would actually need an 11 kilometre antenna to receive it at all, but an 800 kilometre one to actually receive it as music. Consider the problem here. We're searching for extraterrestrial civilizations. The actual search space is huge, so it's not particularly surprising that we haven't detected anybody so far, even if there are any. So let's return to our original questions. Is the Earth alone, and are we alone? Is the Earth alone? Almost certainly no. Are we alone? To be honest, we don't know. We suspect that at least one planet has intelligent life forms on it, although occasionally I do doubt this. But it would seem strange if none of the remaining quintillion minus one did. That's the end of that talk. Look forward to seeing you for the next one. Okay, hope you enjoyed that, and you now know why we haven't detected any extraterrestrials. See you next time. Bye bye.